In this next video about inverse functions, I want to point out a few more things. Let's start out with this. If you remember the picture that we were talking about, here's some domain A, and we're going to take some range B, and f goes from A to B. So here's some x, and here's some y. And so we've defined f inverse as going from B to A. So I'll just write that down. F goes from A to B. F inverse then goes from B to A. And we define F inverse by saying F inverse of y equals x means that f of x equals y, right? So because I know that f maps this guy over to that guy, I know that f inverse maps that guy back over here. And for that to work, we had to have f to begin with being a one-to-one function, and we had to have domain A and range B. Okay? So as you see, because of the way that works out, if f goes from A to B, then of course the domain and the range swap for f inverse. F inverse goes from B to A. Now what happens if you go from x to y and then back again to x? You better end up where you started, right? So there are two equations that basically say that. Your book calls them the cancellation equations, and they involve the composition of functions. So because that's exactly what I'm doing. I'm saying I go here and then I go here. I'm saying I use one function and then I use another function, or I compose the two functions. So that's going to tell me that f inverse of f of x, I do that, I better get my x back. Or f of f inverse of x, I better get my x back. So this first one was the first thing I did here. I take x, I move f to it, and then I apply f inverse, right? So I'm starting with something in this set A. The second one, I'm applying f inverse to something, so I'm starting here. So really, my one point that I have pictured here is y, so maybe I should just say y, but it's easier to remember if we just call everything x. So in the second one, I'm starting here, I go back over here, and then I go over here. I end up with the same thing. But those would be the ones in B. Okay? Now again, so that it's a little bit clearer, we were talking about the one-to-one thing. I have to make sure that my map is defined properly, so I have to know where every point is. So that's why one-to-one is so important. Let me just give you a quick example of that. We can do something like this. Right? Here's a function. My domain is the set of points 1, 2, 3, 4. My range is the set of points 9, 6, 3, 7. Okay? If I ask what f inverse of 7 is, I can look over here and say, well, f maps 4 to 7, so f inverse maps 7 back to 4. That's no problem, right? And I can do that. I can answer quite a few questions about this function with this chart, right? Nothing hard about that. But look what happens if I change my function slightly, and we're going to call it g. And I'm going to change it here. G is still a function, right? Because each point here is mapped to a unique one. But my way back isn't a function, because if I'm going to ask you what g inverse of 6 is, I have two possible answers. It could be 2 or 4. So I can't define g inverse as a function. And the reason that happens is because g is not 1-to-1. So we won't be typically looking at functions like this, where it's just a couple of points. But we will be looking at some functions where this kind of thing happens. Of course, I have my friend x squared. And in fact, you know this part of this story already. So I'm going to go through it pretty quick. But just to remind you, this guy is not a 1-to-1 function. But of course, I need to go the other way. I need to get rid of the square. I have to take the square root. So what do we do to make this function work so that we can actually talk about the square root? Well, we restrict the domain, right? So what we do is take not this whole one, but just this bit, right? So I take f on purely positive things, right? Now it's 1-to-1 and on 2, right? Because I was 0 to infinity. And then I can invert it, right? F inverse is going to be the square root. And as you can see, it looks like that. I should point out too. Did I talk about that in the last video? I might have. I can't remember if I talked about it in the last video. Well, I'll talk about it again. You can fast forward if I'm repeating myself. If you look at this geometrically, what's happened? I've actually flipped over the line y equals x. Okay, this isn't perhaps the best picture. I'm going to do a little bit better job with my pictures, right? That's better. Geometrically, the graph of f inverse is the graph of f reflected, that's what I'm looking for, about the line y equals x. Okay? So, and that makes sense. Geometrically, it makes sense because of what we're doing when we figure out what the inverse is. Remember, we had f inverse of x equals y if and only if. Okay, I had it the other way, right? I'll try to be. Okay, I had it this way. Okay, but you can write it the other way too, x, y, whatever, as long as it's consistent. So we're kind of swapping the roles of x and y, right? We're changing the numbers. We're changing the x and y, and that's why geometrically it does this revolving thing. Okay. Let me just leave this one here, and then in my next video, I'll just go ahead and do an example, show you how to solve for the inverse.